My name is Philip Huttner. I'm the business owner for Mike Shi at DHI. And today we start with the first event of our new Mike Shi webinar series on a monthly basis, where I would like to guide you through what you can do with the model, how it can benefit for your projects or research topics. And in the following webinars after this first one, I will also introduce you how to build your models yourself. So you will get a real step-by-step guide, how you can handle and pre-process your data, and what is the most efficient way for you to build up the model. So I will share my presentation. So today, we would like to answer, what does fully integrated catchment modeling with Mike Shi really mean? That means you probably know a lot about catchment modeling, integrated catchment modeling, but what is the big difference that Mike Shi can do with its approach? The agenda for today will be a short introduction about the modeling principle on a high level, what the typical applications are, where we apply Mike Shi, what are the available modules, what are the possible outputs with this model, in which projects that's what you normally can apply and which questions you can answer. And at the end, you will have the opportunity to ask questions, which I will try to answer the best I can. This meeting can take up to 1 hour. Maybe we are done earlier. We'll see. I will switch between the slides and also some live demo inside the model graphical user interface itself. So what is the modeling principle? Probably everyone here knows it. This is the picture of our draft of the schematic view of the hydrological cycle. We have precipitation coming in, turning into surface runoff or infiltrating, becoming surface water in lakes or rivers, and discharging towards the ocean as groundwater or surface flow. The big thing is that all these processes are highly interlinked. They influence each other all the time and everywhere. And if you then consider also all the anthropogenic applications that we do when we pump out groundwater, treat it, pump it again, infiltrate it again into the groundwater, the irrigation activities that we do, all that processes are becoming even more complex. What do we do as modelers within the water management sector? We normally try to simplify things in a way that we can assess the problems. So in the lower right, you see a very simplified picture now of the hydrological cycle. And then you have different types of models. You have, for example, the 1D, 2D hydraulic models, which focus on the surface water processes, but they normally more or less neglect or simplify to a large extent the evapotranspiration, infiltration, and into the groundwater. So you apply them as fixed boundary conditions or in the constant value. And you try to answer normally problems for flood protection or flood retention. Another field are the 1D, 2D, 3D soil models. They normally work on vertical profiles, one soil column, focus on the unsaturated zone processes. They represent the vegetation already better, and they focus a lot on a vertical high discretization of the topsoil. And again, normally they neglect at least the spatial dynamics in the groundwater, but it's still good enough to answer questions for vegetation growth, agriculture, and irrigation, or simple climate change assessments. Another category are the 1D, 2D, 3D groundwater models. So here you try to neglect the surface water processes, lateral overland flow, and it normally requires recharge as input because it's not computed within a classical groundwater model itself. So it focuses purely on the groundwater processes, which is mainly applied in the water supply sector for assessing groundwater abstractions, groundwater contamination, or within the mining where you have very complex geological dynamics and the top surface hydrology is not as important as a correct representation of the deep groundwater layers. But what we want to do, we want to apply fully integrated catchment models, and they focus on all water processes within one closed water balance. They reflect the mutual influences by using a bilateral coupling approach, and I will explain that later in more details. And which problems can you solve? Well, all of the above mentioned, and you can use them by assessing them in a separate way or together within MikeShe because you have a very flexible modular approach. So what is the history of MikeShe? Actually, it goes back to 1969, where a blueprint by a European consortium in 1976 was at the end drafted, and that describes this fully integrated approach where you really would like to consider all the hydrological processes within one model system. Since then, it's developed a lot, actually since 1998 by DHI. So we are hosting this model, and up today, it's way more than 100 users, more than 1,000 projects in all climate zones, and more than 200 published journal articles. So this is really a proven system, and it's widely used all over the world already. This is the typical sketch that we use for MikeShe, and you can see it's really considering all the processes. So you have precipitation coming to the surface where you have vegetation, then you have infiltration and unsaturated zone percolation. You have a possible 3D groundwater flow model. You have 1D rivers and lakes represented by Mike Plus and implemented with a bilateral coupling. And you have, of course, the diffusive 2D overland flow, runoff and drainage for representing flooding purposes. You even have a demand-driven irrigation from groundwater and surface water. I will show you that later. And you can put to all of the components of the water cycle a water quality model. That means you can simulate contamination, species transport, particle tracking, advection dispersion, and even decay, first order or higher order. So what is the difference? The difference is that other models normally have one engine. They solve one equation. For example, the surface water models, they solve the shallow water equation. Groundwater models solve the 3D Darcy or Richards equation. But what do we do with MikeShe? We couple 4 engines in 2 ways and even put into that the climate. That means overland water can exchange water with the unsaturated zone and with the groundwater and with the rivers. And water can evaporate from the overland flow, from the unsaturated zone, or even from the groundwater if the groundwater is rising above topography. So what you have, it's a coupling framework. It's not only one engine. MikeShe is a coupling framework to completely represent the whole hydrological cycle in one closed system. It allows for water quality simulations, including transport all over domains. It has a graphical user interface, which is not that common today. And the very big differentiator is the bilateral coupling of all these processes. With MikeShe, you're able to represent over-regional catchments with a high accuracy. The biggest models normally don't exceed 5,000 square kilometers, except maybe the Okavango Delta model that we did, which was way larger. So what you do, you solve the 1D, 2D shallow water equation for the overland flow, the 1D Richards for the unsaturated zone, and the 3D Darcy for the groundwater in one model. And everything is based on physical-based processes, and this on regional scales. So no conceptual approaches. And every process runs on its own time step to achieve maximum performance. That means the overland flow can run within seconds or minutes, while the unsaturated zone normally half an hour to 1 hour, and groundwater, depending on the dynamics, the engine will resolve the equations maybe on a daily time step. And the basic philosophy of MikeShe is, with this fully integrated approach, to replace boundary conditions like fixed head boundary conditions or recharge or river water levels, and really put and simulate there the real well-known processes. MikeShe is based on raster data. That means you can pre-process all your input data within rasters. Normally, a lot of the pre-processing takes place within GIS solutions, QGIS or the Esri platforms, and is then used by the model. I will jump soon into the graphical user interface directly, but maybe to highlight that, this is based on MikeZero. So this modeling platform is called MikeZero. And when you open MikeShe, you have here this typical data tree where you can define and configure all your modules. And within the model domain and grid, you can select a shapefile or a DFS file, which is the MikeShe native raster format, and then discretize directly inside the GUI your model domain. What is the cell size, or how many rows and columns, what is the origin, And the good thing is, if the data is pre-processed consistently and with a higher resolution, you can change the resolution before each run. So it's not like you create a fixed mesh, like with Modflow or FeeFlow. No, this is flexible. That means when you start with the calibration process, you go for a coarser resolution to achieve lower runtimes. And later on, when you go into the production runs or for the prognosis, then you would go to a higher resolution. And then, of course, the first thing you will probably start with is the topography, because you needed to simulate accordingly the 2D overland flow processes and also for the depth to groundwater, which influences a lot the evapotranspiration and recharge processes. What are the typical applications with MikeShe? So you mainly serve the sectors where you have conjunctive water use. That means you have competing water users like water supply in terms of a river or a lake, or a drinking water supplier who has groundwater abstraction wells. In addition, together with the agriculture and irrigation, sometimes you have a wetland in there and you would like to re-wet it, a big topic which is upcoming these days. Maybe you want to use MikeShe only for the recharge modeling and import the recharge for FeeFlow. In Denmark and in Florida, it was growing even to a regional water management tool where they are answering nearly every question with MikeShe. And it's used also for the long-term flood management when you want to hold back water in the landscape, infiltrate it to the groundwater, and get the most benefit out of the synergy, lowering the flood peaks and increasing the recharge for other groundwater uses. It's also used for the river engineering when you have a strong groundwater interaction, or for the urban infrastructure when your infrastructure is seeing a lot of groundwater intrusion into your pipe system. Also for the mining, especially when it comes to the dewatering processes. And there's also a special market in Sweden for the nuclear waste storage. And a new upcoming research topic is the plant growth. Of course, you can simulate it yourself. If you need really project support, we would also have a lot of experts on board to help you in your support, in your project. Here you see a small picture of the global distribution. So the blue areas show how much users we have in each country and in each continent, and you see how the model is applied is historically developed historically in different ways, but nearly every topic is covered all over the world. So regarding the available modules, I will jump into the graphical user interface itself because it's a nicer experience. When you open a MikeShe model, I have here a base model. You normally start with the simulation specification. So you can check which process you want to consider, and it's possible to run the model also with a subset of modules. So you could reduce, for example, by turning off evapotranspiration, unsaturated zone, and saturated zone. You could convert it to a basic hydraulic model, as mentioned before. But the real added value of MikeShe only takes place if you use the full functionality and you would like to consider all the bilateral processes. For each module, it is possible that you have different approaches. So there is a more complex finite difference, which is the recommended one, or you can go to a simplified solution, which is the sub-catchment based. For the rivers and lakes, you couple to Mike Plus rivers. I will show that later in more detail. And for the unsaturated zone, you have the most complex solution, which is the full Richards, a simplified gravity flow, or the two-layer unsaturated zone method. For the evapotranspiration, only one solution was possible until this release. Within the next release, we will have a second approach available. And also the groundwater can be simulated in a real finite difference way, which is comparable to any classical groundwater model like Modflow or FeeFlow, or you can simplify it with the linear reservoir approach. But this is mainly of use if you would like to simulate the groundwater originated discharges into rivers. And then when you would like to build up your model, you would go through the different modules. That means within the climate, you have to define at least precipitation rate and reference evapotranspiration, but you could also include snow melt with the air temperature and some basic snow melt functions. Within the climate data, you can distinguish between uniform time series. So the rain will be temporarily varying, but it will be homogeneous for one time step all over the place. You could also make it station-based. So you define single polygons, single zones, and apply each with a time series. Or you can make it even fully distributed. That means if you applied here the grid and you step over time, this is the way or the location where you would apply climate data sets based on radar data or satellite images. And the same way it works for the reference evapotranspiration. The land use is also defined via grid codes. That means you pre-process your polygons, convert them to raster data or your satellite images, and categorize them for certain land use codes like bare land, rivers, forests, or here in this model, highly dominated the agriculture. For each grid code, you can then assign a time series for the leaf area index or the root depth. So you have really a development of the vegetation over the year. In this case, maize is applied. And if you have irrigation activities within your model, it is also possible to define for each cell or for each field certain parameters to include the land use, the irrigation. So for example, if we look into grid code 1, into this field, you have here the option to choose from where the water shall come. It can be taken out of the coupled Mike Plus model, the river model. So then it's really taking water out of the river during the simulation. So you will still see a drop in the river where it's taken out and then applied to the field. You can also choose a single well. So then it will be extracted from a defined groundwater well. You can choose a more simplified shallow well if you don't know where the well is located, which is unfortunately pretty often the case. And then it will be a cell-based approach. That means distributed over these cells, groundwater will be abstracted over the whole area. Or you simply say it's an external source. That means water is coming outside of your catchment and you do not need to simulate it yourself. And it will be additional water to your model. And in the second step, you have to define the irrigation demand. In this case, it's global. You have different options. You can say, I really would like to say a time series or a value which shall be applied. It can be the maximum allowed deficit. You also have the options to apply a crop stress factor, or you will simply want to say, I would like to maintain a certain ponding depth, which is maybe only common in certain continents over the world. In this case, we have chosen a maximum allowed deficit approach based on the field capacity, could be also based on the saturation of the soil. We have a temporal distribution constant. It could be also a time series. And then you have to simply define the thresholds. And the model will itself decide based on the current rainfall, evapotranspiration, and saturation in the unsaturated zone if the model needs to be irrigated. Then you would couple it to a Mike Plus model. A Mike Plus model looks roughly like that. So we jump slightly in a different graphical user interface. And the river model is constructed by 1D polylines that define the branch. And for each branch, you can then apply cross sections. And this will basically define a simple 1D river model. For the overland flow, you need a Manning roughness as for every other surface water hydraulic model. You can apply kinds of values like detention, storage, or initial water depth if you would like to include that. And you can also seal surfaces. That means infiltration into the unsaturated zone, for example, in urban areas, is prevented to some extent. The unsaturated zone module, again, needs one grid as input. And for each grid code, you can define a separate soil. And for each soil, you have the possibility to vertically discretize each parameter. So you define the depth, for which depth you would like to apply which soil. And for each soil, you have to apply a certain unsaturated zone soil parameter file, where you can really apply all the values that you need in order to solve the soil water retention curve, for example, by the Van Genuchten approach. So if you have measured data, you can insert it here. Otherwise, we would also offer always default databases that come along with the basic installation. And to our experience, this is also part of the calibration to adapt and improve these values further. And the groundwater module in MikeShe is called the saturated zone. You can also include wells, you can include subsurface drainage. You have here the option to define geological units. And for each layer, you can apply here different distributions where you then apply a certain hydraulic conductivity. You can do that for separate layers. So if I go here to the pre-processed data, I can show you what that means. At the end, you will have a horizontal hydraulic conductivity for each computational layer that you have implemented in your groundwater module. So layer 1, 2, 3, 4, 5. And you can also make nice cross-sections plots. To visualize really the three-dimensional setting. That's it for the model. I will go back to the presentation and jump over these because we did that here already. And directly go to the possible outputs. So when you have constructed your model and you press run, the first thing you could, for example, use in the most simple way is you use it for recharge calculations. You see here temporally and spatially changing recharge map. Blue to purple means positive recharge. Yellow over red to brown means negative recharge, so evapotranspiration exceeding the total recharge, which is normally the case here in the valleys where you have a low depth to groundwater. And you can also see here the time series that I calculated. The range is here from 0 to 0.8, from 0 to 1, and the strongest dynamics from -2 to 2 millimeters per day. Of course, you have here in this lower areas where you have a groundwater close to the surface. And of course, the higher the depth to groundwater is, the more the recharge time series, the hydrographs are smoothened. You can use these recharge maps directly as input to ModFlow or FeeFlow models if you don't want to simulate the groundwater yourself within MikeShe. That's also possible. Of course, as I said, you have a full 2D overland flow component. So what you can see here, this was a flood protection project we did some years ago, where we were really supposed to simulate the 2D overland flow within MikeShe, the groundwater, a 1D pipe collection system, 1D rivers, in order to design the perfect size and extent and location of a flood retention basin to protect the downstream people living there. You can make nice plots within Mike Plus, showing longitudinal profile plots, cross-section plots, time varying water tables. And you can make really nice plots of the unsaturated zone. So what you see here is, for one certain location, for one cell, the vertical saturation in the unsaturated zone. So 0 is topography, and here you have the depth below topography. And the more red it is, the more it's desaturated, the more dry. If it's becoming dark blue, then you see here that's the current groundwater head within the groundwater module. And in the top layer, you see here stronger dynamics, because you have here a very sandy aquifer, which tends to be always very unsaturated. And in the top cell, you have more loamy sands, which is quite common, at least in North Germany. And what you see here, really the effect on the saturation in the unsaturated zone for single rain events or irrigation events in the summer. So you see here the months at the bottom. So this can be irrigation amounts or can be even precipitation. And you can see how well the precipitation really percolates downwards and saturates the soil to a certain depth. You also have a really time varying groundwater which changes over time and space, like classical groundwater module. You have isolines, and you see also here pretty nice the interaction with the river system. The river system here are the black lines, which is draining the groundwater. As I said, you can also apply the water quality. Here, of course, for example, you have a really an agricultural field where fertilizers are applied. They percolate downwards to the groundwater and then flow downwards within the aquifer to the next lake. And you really are able with this fully integrated approach to track nutrients and contaminations from the overland flow into the unsaturated zone, through the groundwater, into the lakes or rivers and back. It means if the concentrations is traveling downwards, this lake, if it would be connected, you would also see this short circuit or bypass effect that you have here contaminations in the groundwater rising while it didn't travel through the groundwater already here. For the groundwater module, you can also use particle tracking, which is quite convenient if you would like to delineate the subsurface catchments of drinking water wells, or you would like to see, like in this case, we had a case study here with this big lake which was drying out and nobody knew why, from where the water is actually coming into this lake. So you can really trace back where the water originates from. You can apply several species, as many as you want. You can make them dissolved, sorbed, or suspended, or even fixed. And highly underestimated the benefit of having these fully integrated water balances. Since you really include every component of the water cycle, you can say how much precipitation is coming into your catchment. So these are the millimeters per year. You can say how much the groundwater is recharged, like here 47, how much groundwater is really leaving again the catchment, how much is evaporating from the fallen precipitation, and how much leaves the catchment through surface runoff. So basically the amounts that discharge into your river system. You can make them more detailed for each single item. You can lump them together to get a feeling for the overall balances, like here summed up to climate, groundwater and rivers, and can get really detailed insights of how your catchment is working in reality. Coming to the project applications. Where do you use normally MikeShe? In the water supply sector is a big market for us because, for example, you would like to know, again, this project, we were mainly focusing on this lake here. The question was, here is a big drinking water supply. If you turn off the groundwater wells, how would the water level in the lake develop over time? Is maybe the increased abstraction from the groundwater here the reason for the dropping water levels within the lake? And yes, to some extent. So blue is the calibrated reference state, and yellow is the scenario run without the reduced groundwater abstractions. And you see the yellow one is slightly higher like as the blue, but you would not maintain the average water level that was observed in the past because it's an overlapping of several processes like climate change and the groundwater abstractions. And you can make, of course, since you have a full 3D groundwater module, very nice differences plots to see if you turn off the groundwater wells, how much of an effect would it have to the groundwater in terms of space. For the same project we also did, you see here still the lake in the lower left corner, some land use change assessment for the upstream subcatchment. Independently of if it's a good idea, we were supposed to investigate what happens if you turn or change the forest, the land use equals forest, to greenlands, which is supposed to be reduce the evapotranspiration and therefore increasing the recharge. So you can simulate this also. You'd simply change the leaf area index and root depth or your grid code for this area, run the model, and see here, yellow is indicating a low recharge rate and blue for the scenario a higher recharge rate. So you can really increase the recharge by changing your land use. So every land use assessment that really needs a fully integrated approach can be assessed with MikeShe. And we did, of course, the same graph. So we show again, blue, the reference state model, and green, the scenario, how the lake water level would develop over time. We could plot the same for the groundwater hydrographs. In this case, we did it as a spatial differences map. So you can see here the subcatchment where we changed something led to higher groundwater levels in average. Another very big project recently finished in London is the River Thames scheme. Here we are answering questions related to the long-term flood management and river engineering. So you have here one part of the River Thames where some side channels are supposed to connect several lakes into a chain, which then should work as a flood retention basin. Another project application was done here in Bavaria, South Germany, where we were supposed to re-wet, let's say, former wetland that is today used as agricultural field laboratory. And they would like to rise the groundwater again by applying weirs and several structures, while still being able to cultivate crops that are still able to grow with a low depth to groundwater, so a high groundwater table. So we did a very, very, very detailed calibration. You can see in here in black, here is 0, here's the topography. In black, the measured groundwater head with probably an hourly resolution, and in red, the simulated one. So you still have this offset during the hot start when the model starts to achieve an equilibrium state. And then you can see really that groundwater is able to rise above topography, turn into overland, and flow downwards over the topography within your model catchment. And you can see the strong drawdowns in the summer where evapotranspiration is exceeding the recharge. And you see really each single precipitation event within the model. So whenever the groundwater rises in the model, of course, you trigger higher evapotranspiration because capillary rise is leading to upwards water flows. And once it was calibrated, we were able to dimension several measures. I do not need to go into the details, so we have designed here new shafts that were preventing the implemented drainage pipes of draining the groundwater further. We implemented a new weir and even an overspill pipe. And with all these measures, we were able to help our client to show how much the groundwater level can really be lifted up in order to re-wet this wetland. And I saw that one of our best clients is also attending this meeting. Happy to see you here, Carsten. With him, we did also a very nice project in North Germany, where we are asked to support the Agricultural Society or Farmers Society Association, how to improve the groundwater recharge and therefore the available groundwater resources for possible new permits in order to abstract more groundwater. So you can see this area is highly dominated by agriculture. And at the end, we were helping together with our client to suggest some new weir locations to hold back water in the groundwater and therefore increase the recharge. So here we were serving for the water supply and the agriculture and irrigation sector. And I would like to choose this model to show you a nice use case. So going back to the model you've seen recently, you have the option here to directly print out time series for several items. So of course we had included all the groundwater monitoring stations that we were supposed to calibrate, but I added also here in a certain location around here within the river some more observation points. And then for this location, where I define X and Y coordinates, I can directly show for each cell, like here, in the river called Döringbach, the depth to groundwater. So I'm start at minus round about 2. It rises in Germany throughout the winter months, and it drops throughout the summer months. You can plot the actual evapotranspiration, which is simulated by the model itself. It's close to 0, of course, in the spring and in the winter, and rises up to 6 to 8 millimeters per day in the hot summer months. You can even differentiate between the real soil evaporation and the transpiration by vegetation or crops. They together would sum up always to the actual evapotranspiration. And you can even also look into the irrigation amounts. I have put here one time series output into an agricultural field, and you see here in the dry summer months, some irrigation in millimeter per hours is required. I tweaked a little bit here the parameters to get higher values, so this is not a calibrated or real result anymore, but it's better for these showcases here. Since you have a bilaterally coupled model, you can do the same for the river model. That means you can put at each drainage location where you have applied a certain cross-section the water level or the discharge. And this is already called where, because I would like to go with you through short scenarios and show you how these would develop then. So what you can see here is the upstream water level calculated within the river. You see it follows quite nicely the groundwater depth, which makes sense because they influence each other. They are dependent on each other, and they should not be simulated separately. And you also see here the peak during a strong rain event, 1st of June. You can also look at the same way. Up. Oh, it's hanging. Give me a second. Water levels and discharges. So you see here in average, this river shows values between 120 to 250 liters. The peak goes above 300 liters. And in the dry summer months, you have only a very low base flow, and the discharge goes down to 10 liters per second. So looking now into the river model, which is bilaterally coupled to Mike Xi, we can add here a where. That means, in this case, I implemented it already. I go into my map, zoom into the desired location. Here you see this gray point, and create pretty easily a new gate. Then I can go to the corresponding tab and define the values of the where here gates. You see in this plot already the upstream and downstream cross sections, so that you can construct the where in a where that it makes sense. For this scenario, I included a where width of 3 meters. A max gate level until it which can be pulled up is 48 meters, and the minimum level is 446.5. You can distinguish between overflow, underflow gates, radial gates, or even a sluice gate that can be overspilled and underspilled. And then you couple this one to a copy of your Mike Xi model. Here it's called with where. And now I look into the results. Let's start with the river results. What I did now here, the dotted values, the small points, these are the model results from the initial reference run without a where. But defining an let's say a maximum value of the where of 48 meters, of course, rises the water level. The same way, we can look into the discharge. which obviously does not change too much. It changes a little bit in the very beginning because the retention volume upstream of the weir needs to be filled up. That's why in my scenario, the discharge is way lower until the water level rises until the top of the weir and then is able to spill over the weir. And the difference that you can see in here now, this is the amount of water that you hold back in the groundwater. So that's the reduced drainage within your river system. How does that look like in the model, in the river model? You can create here nice longitudinal plots. So you can load your results here, the river system, and via setting here flex, I can add here a new section plot here. And in red, I can even overlap two result files. So if I go here one step forward, in blue, you see the water level that is simulated by the model system for the reference state. And in red, you see the impounded higher water level with a weir. And you see, of course, here we have a higher rise within the water level. And you can even visualize this effect again, also in the groundwater component. So if I go again to the whole view, I loaded in here in dark blue, maybe not the best color now, the river system, and I loaded both groundwater heads results for the same location. The blue isolines are showing the groundwater heads within the reference model, and directly below it, because for the first time step they are overlying, you can see in red in a minute the isolines simulated for the groundwater module. And I can run that over time. And even visualize the differences. That means when the weir is pulled up, we have now a rise in the groundwater because less water is drained. And you can even see how the groundwater isolines would develop over time. And this was now a very detailed assessment, which we did for several locations within this big project. I also prepared two other scenarios. I made a copy of the reference model and changed the vegetation here from maize to onions. So you can see they are growing already earlier in the season, and then they are cut off, and then they are growing again. So you can really change here the crops that you would like to grow within your model. And within the fourth scenario, I added one more well inside this location. So I'm holding back water within the river with my weir, but then in the fourth scenario, I include a new well, which is then possible to use this water, which I'm holding back, maintaining within the catchment. And what you can do within MikeShe, you have an incorporated water balance calculator. Since you run here a fully integrated model, everything is solved for each model cell, and you can create quite nice water balance plots. So if I go to the next slide, you get directly a good overview. This is the 1 year balance of what happens within your catchment. So this is now the reference model, nowhere. We have a precipitation of 600 millimeters. And now we would like to compare it with the maize to onion setup. And what you see here, if we look at the irrigation and the evapotranspiration, they are changing, of course, because we have a different crop. That means a different leaf area index distribution, a different root depth distribution. So in this case, the evapotranspiration is rising slightly, and also the dependent irrigation amounts. If you compare it to the scenario, both are cultivating maize here, nowhere and with a weir structure. And we look now into the saturated zone, so the groundwater storage change, which is dried out a little bit in this scenario, but increases here, of course, because we hold back water within our aquifer. And also the base flow to river is reduced because less water from the aquifer is drained by the river system. In the same time, you have a rise in evapotranspiration, of course, because you have a smaller depth to the groundwater. So you will have more evapotranspiration triggered in this small subcatchment. If you compare this one now with the scenario with a new groundwater well, you see here was only a small pumping needed for the irrigation, but since we have implemented a new well, you have here again a higher pumping rate. And of course now the evapotranspiration goes down again because the groundwater is lowering the groundwater head within this subcatchment. And at the same time, the base flow will be lowered again. But the river loses more water because the gradient between river and groundwater are changing. So even if these are only small numbers, I think it really good highlights how this fully integrated approach is considering all the processes and how they influence each other. So if you would ask me, MikeShe is unique because you can simulate groundwater, surface waters, and evapotranspiration in one closed system. You can consider this bilateral exchange in both directions, include complex 1D rivers and pipes, including structures with logical operation rules, simulate contamination traveling through overland flow, groundwater, and rivers, apply physical-based approaches on a regional scale over many years. And you have a powerful graphical user interface for the pre- and post-processing. So if I was successful and you're now excited about MikeShe, stay tuned. Register for the new upcoming webinars where I would like to further introduce you how to build a MikeShe model yourself for your project. If you would like to know if this is really good for your project, feel free to reach out directly to me. And not up to date right now, but I will fill out this new online manual over the new weeks and months where you can guide yourself through how to build a model step by step. So feel free to connect with me on LinkedIn, then you will get the news related to MikeShe always directly. And of course, I encourage you highly to register directly for the next webinar, which will be end of December. You find it within our training portal, and there I will start from scratch how to build a model MikeShe yourself. Feel free to really mail me afterwards, that's fine. Thank you very much for joining. I enjoyed it a lot. Very good questions. And as I said, looking forward to see you again.